Greetings and welcome back. Today we have a very exciting topic, which is chirality. I'm not being sarcastic. I really think that chirality is one of the coolest things we do in organic chemistry. It's a concept that can apply to every physical object that you can possibly imagine, and yet it's one that we don't usually entertain the notion of. So, what is chirality? Let's jump right in. Chirality literally means like your hands. The Greek word chir is hands, and so this is like your hands. So we ask, is something like your hands or not like your hands? And what that means is chiral, the definition of something that is chiral, has a mirror image that is not superimposable. So, if you will, look at your hands. Your hands, barring any minor imperfections or freckles or anything like that, your hands are mirror images of each other. So if you hold them out in front of you with your palms facing up, you'll notice that on the left hand and the right hand are complete mirror images. You can imagine a mirror directly straight in front of you, shooting straight out of your nose. And so what you can see is that if you took the left one and took the mirror image, you'd get the right one. But if you turn your right hand around and try to make it exactly like your left hand, well, they're not exactly the same. So you can put your thumbs both off to the left, but on your left hand, your palm is facing up, and on your right hand, it'd be facing down. You can try spinning your arms around in weird ways, but your hands are not identical. They are mirror images, but they are not superimposable, meaning you can't rotate them around to become the same thing. So in chemistry, we have a lot of molecules that are chiral, in that their mirror image is not superimposable. But we also have a lot of molecules that are achiral. And an achiral molecule, A meaning not, is that they are not like your hands, and being not like your hands, their mirror image would be the same thing. So their mirror image is identical. We'll talk about in class some real-life examples of things that are achiral, some real-life things that are chiral, but I would encourage you in the meantime to kind of look around at things. All right, so largely we'll be applying this to chemicals, but it's a really cool thing to kind of think about what you're wearing, what you're eating, and whether or not these things are chiral or achiral. All right, so let's think about how this applies to chemicals. I'm going to use the example first of, let's use 2-chloropropane. So we'll do a 3-carbon chain, and we'll put a chlorine attached to it at the middle carbon. All right, so as a tetrahedral carbon in that center, I would have 3 carbons in a row, chlorine's coming off the top, but I'm going to put my H in back here so that we can kind of take a mirror image of this and see what it looks like. All right, so if we do a mirror image, essentially what we would do is imagine kind of a mirror right in the middle there, beautiful mirror. And we're going to basically go through the looking glass, and we're going to flip this around. So again, kind of like you did with your hands, if you hold your hands out palms up, you'll see that they are mirror images of each other if you had an imaginary mirror straight in the middle, but up is still up, right? Your palms are both facing up. Your fingers are still away from you, so back is back. But what's flipped is just right becomes left and left becomes right. So that's what we're going to do in this case. So let's draw the mirror image. The mirror image would have the chlorine still up, and it would still have the back stuff on the dash, and the front stuff would still be on the wedge, but right would become left and vice versa. So I will put my methyl on the left instead of the right. I'll have the methyl on the wedge be on the right instead of the left, and I'll have that H in the back on the right instead of the left. So we can look at these two molecules and ask ourselves, are they superimposable or not? Well, as we look at them right here, they don't appear to be exactly the same thing. But superimposable means that you could rotate them around and see if they're still the same. So let's do a little rotation. I'm going to leave the left one, the green one, exactly how it is, and I'm just going to move around and mess around with the mirror image. So let's imagine that that bond that's straight up and down here is going to be my axis, and we can rotate around that. So I can spin the H over here. The methyl will go to the front. This guy will move back a little bit. And so I can draw this again, and it'll be the same molecule, the same kind of mirror image, but I'm just rotating it. So if we rotate it, I can push the H back here, it would push a CH3 up and to the front, and I would have a CH3 down. And you'll notice that at this point, this structure, which is the mirror image, and this structure, which is the original, are indeed identical. And since the mirror image is identical, we would say that this molecule is achiral. It's not like your hands. In your hands, the mirror image is not the same thing. Your left hand and your right hand are different. But in this case, with these chemicals, this specific molecule, which was again 2-chloropropane, the mirror image of it is identical. Therefore, it's not like your hands. So we would say that this is an achiral molecule. All right, let's do one more example. So this time I'm going to do something very similar, but we're going to do 2-chlorobutane instead. So I'm going to draw this out. I'm going to put the chlorine on top again, and I'm going to put 1 carbon off to the left, 2 carbons off to the right, then I'll put an H in the back. All right, so let's take the mirror image of this guy. So here is my mirror once again. And when I draw the mirror image, which I will draw once again in yellow, the top will stay top, and left becomes right, right becomes left. All right, and then we can rotate this guy around. So the one that I have now drawn on the right, I'm going to rotate it a little bit. And it's hard to imagine all of the possible conformations, but what I'll do is kind of put the ethyl group in the same spot. So I'm going to rotate this all the way around and rotate these guys all the way around. And if I do that, then for my mirror image of the original, once I get those guys off and to the right, well, if I rotated the H and the CH3 all the way to the right, it's not a flip, but a rotation, then the H that's in the back would become rotated around to the right, to the front, sorry, the left to the front. The CH3 would be rotated back here. So once again, this is going to be easier to do with chemical models that you can hold in your hands. But notice that at this point, I've got 3 things in the same spot. I've got the chlorine in the same spot, I've got the ethyl in the same spot, and I've got, well, that's it. And the H and the CH3 are not in the same position. And no matter how I rotate this guy around, it cannot be exactly the same as this. So therefore, we can say that no matter what you do to the mirror image in this case, it is not going to be superimposable. Therefore, what is on the right and what is on the left are not superimposable. So just like your hands, the mirror image is not identical, it's not superimposable, so therefore this is a chiral molecule. And this is also a chiral molecule, but because these are not superimposable, they're just not the same molecule. These are 2 completely different molecules. And we'll talk more in class about the differences, and actually we'll see a little bit about this in lab as well. But what's really cool about these guys is that they're very similar, right? They're both 2-chlorobutane, but they have one strikingly different physical property, and that is that they're going to rotate light in an equal and opposite direction. So they'll have the same melting point, they'll have the same boiling point, they'll be the same color, they'll be the same phase, obviously, at any temperature. But when we dissolve them, they'll rotate light in opposite directions. So it's a really kind of wacky thing, but these molecules have differences. They have slightly different physical properties when it comes to light rotation, but by and large, all the rest of their physical properties are going to be identical. So they're very cool, and this is something that wasn't figured out for, as you can imagine, thousands of years of understanding chemistry. So chirality is a relatively recent invention, or not an invention, but a recent understanding of chemicals. So there's one way that you can tell whether or not a molecule is chiral, and it actually has to do with this carbon right here in the center. If there is a carbon in your molecule that has 4 different substituents, so notice that that carbon right there that I labeled in yellow, it has a chlorine, a methyl, an ethyl, and a hydrogen. If a carbon has, or really any spot, but usually carbon, so if a carbon or other atom has 4 different substituents, it is a chiral center. Oftentimes we call that a chiral carbon. And so those are the only carbons that can end up actually being chiral. And what we'll find is that for a molecule, if a molecule has exactly 1 chiral center, then the molecule will be chiral. And so sometimes, oddly, if a molecule has multiple chiral carbons, it might be chiral, it might not. If it has 0 chiral carbons, it might be, it might not. And that's something that we'll play around with in lab this week. But in general, what you can always know is that if a molecule has exactly 1 chiral carbon, then the molecule will surely be chiral. All right, so this is, again, I've given you kind of a thought experiment to play around with for the next hours to days, depending on how long it is until class. But this is a really neat new concept, chirality, and we will talk about it together. So I will see you soon. Thank you very much.